Hello, hello, may I audible? Hello, hello, may I audible? Praful, Sumit, Vineet. Anybody tell me, may I audible?
येतोय सर आवाज येतोय.
Okay, screen is visible.
येस सर.
Okay, in last lecture we have started chapter implementation of object methodology and techniques. So implementation of OMT. In this chapter, we have studied use of programming language and database system, object-oriented style, features of object-oriented languages. Then next point, applications of OMT like object diagram compiler and computer animation. So first application we will see in detail. So object diagram compiler. So in this application, we will see what is the background of object diagram compiler, what is the problem statement, analysis, system design, object design, implementations, and what we will learn in this object design compiler, object diagram compiler. So object diagram compiler background in this compiler provides natural applications for the OMT methodology. Most compilers are batch programs that consist of one or more passes, and each pass works towards goal of transforming the input to the output. For example, C compiler may accept an input file of ASCII character. The successive passes may parse into tokens, abstract the intended semantics, generate codes, and then optimize the code. Users expect that the compiler will carefully check its input during processing. The more errors the compiler can detect, the fewer errors will be encountered during program execution. So in this part, in this the development of compiler object for object diagram, here we have taken the example as bill of material BOM, bill of material applications. So the compiler is a batch program that accepts an object diagram as input and produces the RDBMS schema as output. The compiler input is limited to object diagrams of bill of material problems because because of the special error checking built into the compiler. The compiler has served into two purposes. It solves the immediate problems of target applications, and it was important a milestone in our continuing work on automating the OMT methodology. So object diagram compiler illustrates several concepts. The compiler architecture consists of four passes that step through a series of internal models. There are many relationships and functional dependency within a model, but few between models. So The here we have taken example of bill of material. Another example, General Electric has internal applications that configure product assemblies. Business practice for the applications is that the customer specifies product function. The manufacturer must devise the corresponding product. For example, the customer might order a lawn mower, is a name of product, that is a lightweight, inexpensive and energy efficient product. The manufacturer may fill order with mower has 1 horsepower gasoline powered engine, 45 centimeter diameter aluminum deck and non-mulching blade. So the list of parts selected by the manufacturer to build the product is called as a bill of material. A bill of material is a tree of direct indirect parts that compose an assembly. The literature often refers to bill of material as a part of explosion problem, and the bill of material are often printed on intended parts list where the intention corresponds to the depth in the hierarchy. So this is the figure. In last slide we have given explanation of lawnmower. So it have serial number LM16G, engine engine name E1, 1 horsepower gasoline powered. Then what is the piston? Piston description P1, 5 centimeter length, 0.5 centimeter diameter. Then carburetor carb 9. Then wires width of 15, wires width 15, quality 4, oil resistance, etc., etc. These are related functions, related the attributes of the engine. Then deck D16, 45 centimeter diameter. Then aluminum material. Then in case of blades, blade 16, 40 centimeter long, non mulching. Then what about wheels? WH3, solid rubber, 8 centimeter diameter. These are description related different parts, deck, blade, wheels. So engine, deck, blade, wheels relate. These are the parts or these are the attributes of the lawn mower. Okay, this figure shows the bill of material lawn mower. The first value listed after each part is part number. Suppose engine E1, this is the first value of engine, piston P1, carburetor carb 9, wires W15. The first number is part of part number. Thus the mount power LM16G has engine E1, deck D16, blade B16 and so on. The part properties has this part numbers, piston P1, carburetor carb 9, wires W15. These are the part numbers. So this chapter or this part describes the portion of new bill of material configuration system. A subsystem is called as object diagram compiler. First, we draw an object diagram of bill of material parts explosion with an ordinary graphics. The first, we draw object diagram of bill of material parts explosion with an ordinary graphics editor by carefully placing many lines, triangles, boxes, text strings, and other primitives. The box The object diagram compiler then processes the object diagram and ultimately generates DBMS commands that create tables and indexes. Whenever we change the object diagram, we return the compiler and generates new database commands. Thus, the object diagram is a living document. Thus, the object diagram is the living document. N- Thus, the object diagram is living document. The object diagram compiler simplifies documentation and database schema generation by using the same source document for both. Our success with the object diagram compiler has motivated further work towards developing more comprehensive tools for automating the OMT methodology. So second point, up till now we have seen the background. The second point is what is a problem statement about any program. So here we have taken example bill of material. So what is the problem statement of bill of material? So this figure shows the object diagram compiler towards bill of material into database commands and check the input errors. So in figure, so bill of material object diagram with graphics editors. So then this input forwarded to the editor's statements. Then in graphics editor statements, object diagram compiler. So compiler compiles that statements. If there is error, send error message and remaining part sends to the database commands store as data dictionary. Then this problem statement have three parts: compiler input, compiler output, miscellaneous requirements. So we will study deeply in these three parts. So first, compiler input. The compiler must read an ASCII description of a bill of material object diagram produced by a general purpose graphics editor. So we use a frame maker, but others such as Magdraw or Interleaf are also suitable. The graphics editor must be geometric shaped, not a pixel shaped. Geometric shaped in that means rectangle, ellipse, squares, diamonds. So the compiler input is analogous to the source of the conventional programming compiler. The figure shows the sample of bill of material object diagram of lawnmower. So this lawnmower have number and more width. So it is associated with blades and engine. So blade have blade number, blade length, and mulching. Similarly, engine have engine number, motive power, horsepower, etc. This is the sample object diagram of bill of material. So then object diagram must support basic object modeling constructs. Any object diagram consists of class, binary association, binary aggregation, generalization. The compiler does not need to support modeling constructs that are not needed for our bill of material applications, such as qualified associations, n-array relationships, and operations. Here we have taken 4 to 5 examples. Suppose I want to draw a rectangle. So Start class rectangle. Rectangle have width, so B rectangle, width, length, then height. So these are the properties of the rectangles. Then this this is start of rectangle class. Then this is the end of rectangle. Same. Next class is text line class. This is start of class. Then so starting to write a text line, it have its origin TL, that is text line origin. So point 58 inches to point 50 point 5.83 inch. Then text line must be center left right justified alignment. I have selected alignment, TL alignment center. This is start of origin, end of origin, start of alignment, end of alignment. Then what is the type of font? So start of font. Then suppose I require font bold, F bold, yes. Then end of font type, then font. This is end of font. Then what is type of string? Then string blade, and this is the end of text line. Similarly, I want to draw another rectangle. Then these are the description for another rectangle. I want to draw another text line. Then this is description for another text line. This is then I want to again draw another text line. This is another text line, and so on. This is a description for compiler input. So the compiler must read an ASCII description of bill of material object diagram produced by general purpose graphics editor. We use a frame maker. So graphics editor must be geometric shape, not pixel based. The compiler must be analogous to the source code of conventional programming compiler. So in last slide we have seen the same figure of bill of material. This is sample object diagram of bill of material. Then next point is compiler output. The compiler must produce a series of database commands. This output is executed as a script file to load a data dictionary. We used the Oracle DBMS, but any RDBMS that support the SQL language is suitable. The compiler must generate association names and determines how to implement the relationships. The compiler output is analogous to the direct code of conventional programming language compiler. The object diagram compiler stores its output in a data dictionary custom designed for bill of material application. We used this custom directory dictionary rather than a database dictionary because we use a bill of material specific extensions. Then third part is miscellaneous requirements. The object diagram compiler was support to further requirements on development time and performance. The compiler has to be developed quickly in 4 months or less than 4 months. It was the part of larger bill of material generation project, and we didn't want to divert our attention, our requirements on execution time were more lax. An execution time of 2 hours or less is adequate because the compiler is a batch programming that is only run at system setup time. The compiler is not used for day-to-day generation of bill of materials. As it turned out, because of skillful software engineering, performance was much greater or much better than required. Then compiler must detect input errors but need not correct the errors. For instance, a class name must be unique and have less than 31 characters and begin with alphabet character. This is the minimum requirement in case of class. In programming languages, the compiler must not abort when it encounters user errors. The compiler must accept bad input but keep running so that the user can detect multiple errors from a single run. The compiler must tolerate imperfect connection. Since object diagrams are prepared with the general purpose graphics editors, it is difficult to align and precisely connect everything. The compiler must accept input that looks correct when printed on paper. Also, the compiler must detect mistakes that are not visible, such as superimposed drawing components. The compiler must isolate dependencies on graphics editors and RDBMS within one or two modules. Then the compiler can be ported without major rewriting. Then third parties analysis. Whenever you start a project, there must be object of that project, or what is the aim of that project, then what is the problem statement, and third parties analysis. The analysis is a first step towards solving the problem statement. It quickly became apparent that the difference in level of abstraction between input and output was too great to span in a single step. We decided that it would be best to use several passes. This conclusion is not surprising since many compilers require multiple passes. The disadvantage of multiple pass approach is that developer must prepare multiple objects and design multiple compiler phases. So if there are many passes, then there is a tedious task to developer or designer to develop multiple object models and design multiple compilation phases. The advantage of multiple classes is the complexity is addressed in a divide and conquer fashion. The resulting code is easier to port since graphic editor and the DBMS dependencies are isolated in small portions. So this figure is functional model of object diagram compiler. So here input is ASCII description of object diagram, then sent to the parse graphic editor which pass the languages graphic editor language, then sent to the geometry model which model is related to that input, then extract the connectivity. So send to the connection model, then it pass to the abstract bill of material entities, then send to the internal data model, then send to generate commands, and then pass towards the output command to load database data dictionary. This is the different functions. First input, then parse or send to the graphics editor, then send input towards geometry models, then extract the connectivity, then send to the connection model, then abstract the bill of material entities, then internal meta models, then generate different commands and send to the data dictionary commands to the load database data dictionary as output. So this analysis is divided, or it has seven parts. These are seven steps. So parse graphics editor language, this is the first step. Then geometry object model, this is the second step. Then extract connectivity, third step. Then connection object model, fourth step. Then abstract bill of material entities, fifth step. Then internal meta model, sixth step. And generate database commands, this is seven steps. So from input to output there are internal seven steps for analyzing that input data and generate the output. So we'll study these seven steps in detail. So first step is parse graphics editor language. The first pass reads the raw diagram FrameMaker file generated by graphics editor and builds the geometry model. The first pass corresponds to lexical analysis in a conventional programming compiler. This pass requires little analysis effort beyond figuring out the correct BNF syntax for the graphics editor language. Our development for the BNF grammar for the graphics editor was aided by the vendor documentation. Then second pass is object geometry object model. In geometric object model, this is the figure regarding the page. This is the class page. It have properties, page number. So so each page may be in different shapes. It may be in elliptical form, rectangle form, polyline form, polygon form, or text line form. If it is in ellipse, then it have attributes fill. If it is ellipse and rectangle, it have both. Ellipse or rectangle both have the same property as boundary. In case of ellipse, what is a major axis, what is a minor axis? In case of rectangle, what is length, what is width? So boundary may be a top location, left location, width, height. These are the properties regarding the ellipse rectangle. In case of polyline, polygon, or text line, in case of text line, it have properties is alignment, whether it is left, right, justified, and center. So in case of polyline, polygon, or text line, so same point is same part is a point. These three have same part. Polyline, polygon, or text line is point. But in case of polyline and polygon, These two are ordered points, and each point have x-axis and y-axis. Then in case of text line, another part is a font. What is the size of that font? Whether it is italic, bold, underline, whatever. And this is the geometric object description model. Example is page. So figure summarizes the geometric model. We have omitted the same some class associations and attributes in order to converse space and simplicity explanations. The geometry model represents a diagram as series of graphics primitives and is convenient form for further processing. The geometry model regards an object diagram as simply a picture. The graphical objects such as ellipse, rectangle, polylines, polygons, and text lines, which can coexist but have no interrelationships. We derived the geometry model directly from the BNF grammar of the graphics editor language. So graphics editor that we used organize the components by page. Text line is a single line of text that may be placed anywhere on the page, and a text line has font and alignment. Text line have font and alignment and originate at a point, and each font describes a text size and special features such as italics, bolds, and underlying. The geometry model includes page number for use of error messages. So then geometric shapes, ellipse, rectangle, polyline, and polygon capture graphical information in object diagram. Ellipse have location and bounding rectangle. An ellipse may have a hollow fill or a solid fill. Rectangles have a location in case of width, height. Polygons are composed of straight line segments that connect a sequence of points. A polyline is an arbitrary sequence of lines, and polygon is a closed geometric figure. So the geometric model for our example, first we have seen the example as lawnmower example, which contains the following objects. The lawnmower consists of 6 rectangles, 11 text lines, that is 3 bold fonts and 8 normal fonts, 2 polygons, that is diamonds, 2 ellipses, or which happen to be a circle. Ellipse is a part of circle. A circle is a part of ellipse. Ellipse consists of two axes, major axis and minor axis. But in case of circle, both major and minor axes are equal. A ellipse in which both major and minor axes are equal, then it is called as a circle. Then two polylines, the vertical lines between lawnmower and beds, lawnmower and engine. Then next point is exact connectivity. Up to this geometric model, we have seen the first pass. Then in second pass, the consolidates a raw geometry, specifies size and shapes, and detects intersections and attachment of geometrical primitives. We call the output from the second pass to the connection model. So figure in previous figure or figure in next slide represent part of raw data flow diagram of this pass. Ellipses, rectangles, polygons, and text lines from the geometry model are input data stores in the functional model. Every class and association in the connection model is input of one or more functional model processes. Recall that during analysis we do not specify algorithm but specify the effect of processes. So this is the figure. So in this figure find the nearby block or net text diagram. So this is related with the text line, polygons, polylines, rectangles, ellipse. So this figure is a group of contiguous rectangles are recognized as blocks. These are the blocks, text lines, polylines, rectangles, ellipse. Then block reference pairs, ball node pairs, net text line pairs, block text line pairs. These are the blocks, and each block and group of inserting lines recognized as nets. The connection of two ellipses. This is first ellipse, this is second ellipse known as nets. These are the nets. So ellipses are classified into multiple balls or sheets cross references, and each multiplicity ball is associated with node. Each reference is associated with block, and each text line is bound to the nearest block or net. Then connection object model. In previous slide we have seen the page number. This is the figure page number. In this figure, page may be in geometric models such as ellipse, rectangle, polyline, polygon, text line, and it have so and so properties we have seen. So the same diagram is classified connection with object model. Page have page number. So these have reference. So reference of block name with some text line. Each block have node or each node is associated with block, net, point, diamond, ball. These are interconnections of one object to another object. This connection model summarizes in this figure bridge, the geometry model, and internal meta model. Classes that are shaded and carried forward from the geometry model. The connection model regards an object diagram is a topology, a collection of blocks connected with nets. Blocks and nets have attached geometry and text. Blocks and nets. This is blocks, nets attached to the geometry as a text. This block is attached to the text which have alignment and string. Net also net name attached with the text. Net have the polygons, polylines. Then page may be a triangle, so it have net name, polyline. So triangle have number of lines, that is maximum 3 lines and minimum also 3 lines. Then the connection of our lawnmower example contains 3 blocks: lawnmower blade engine, 2 nets named lawnmower blade and lawnmower engine, 4 nodes, 2 diamonds each associated with node, 2 solid balls with associated with each node. The lawnmower block is associated with two text lines: mower.number and mower.width. Similar association occur for blade and engine. Then abstract bill of material entities. This is the third pass. The third pass raises the level of abstraction. The graphical symbols of bill of material diagram have more meaning than their mere shape. The block denotes a class. A net represents a generalization or association. Pass three bands together cross references to classes and verifies uniqueness of names and classifies relationship types. Pass 3 applies hard-coded rules for mapping relationships to tables. The second and third pass correspond to the semantic analysis in a conventional programming language compiler. The functional model for this pass is complicated by extensive error checking. Much of this error checking derives from using general purpose graphics editor to construct the input object diagrams. In general, the user can make many diagramming errors such as dangling association lines, duplicate class names, and class blocks without names. The object diagram compiler also checks for error peculiar in the bill of material generation. The pass-3 functional model is too large and complex to display here. Then sixth point, internal meta object model. So this figure summarizes internal meta object model that captures the meaning of bill of material diagrams. A bill of material database has many class and association tables. Each class table has many attributes. Suppose this is a class block. It have attributes block name. Then this class table is a class name and its attributes as a name, then primary key name. So it is associated with class table associated with block, class name associated with role attribute. Then another class is attribute associated with attribute name. So it have two parts: role attribute and non-role attribute. And non-role class table also associated with non-role attribute. So this is the internal relationships of different classes, different attributes. So an attribute may be a role or non-role attribute. The non-role attribute belong to exactly one class or association table. The non-role attribute belongs to exactly one class or association table. The role attributes appears in many class and association tables. Role attribute connect together the various tables a class attributes with all blocks that refer to it. Each membership associates with one net. So a bill of material database also has many relationships. Each relationship is either a generalization or an association. Association may be further refined into aggregation. Each generalization has one role attribute that denotes the superclass and many role attributes that denotes the subclass. A discriminator indicates which subclass pertains to each superclass instance. Since bill of material generation only uses binary association, each association has exactly two roles attribute. A association may have zero or more non-role attributes. Then for our example, lawnmower example which contains objects three class tables named lawnmower, blade, engine, zero association table, three role attributes that is mower number, blade number, engine number, non five non-role attributes, two aggregations, both association and aggregations, and zero generalization and zero link values. Then seventh point, the fourth and final pass transforms the internal meta model of database meta model. This process is simple because the internal meta model is similar to the database meta model. The last pass is analogous to the code generation in conventional programming language compiler and produces the desired output of devious commands. Then system design. First, we have studied objective. Second, we have studied problem statement. Third, we have studied analysis. Then fourth part is system design. The choice of system architecture for the object diagram compiler was straightforward and directly follows from overall functional model. The object diagram compiler consists of sequence of passes that transform between layers. We select a closed architecture where each layer can only access the objects in itself and immediate preceding layer. The advantage of closed architecture is increased information hiding which simplifies debugging, extension and portioning. The disadvantage of closed architecture is relative to open is loss of efficiency. The object diagram compiler efficiency is good because of the careful design. The models shows the linkage between object model as shaded. Thus, the class table is internal meta model reference to block in the model. The object diagram compiler complete the in full before proceeding it. The use of there is a little locality of the reference of our below material diagram. So, so object diagram compiler manages all data in memory. Then input is a file, output is also file. There is no need to make intermediate data visible outside the program. Since the program has closed architecture, we considered deallocating objects from earlier passes that are no longer needed to recover memory space. We didn't allocate objects because of the extra logic required and fear of dangling pointer bugs. Memory consumption has not caused us any problem to date. Implementation of control is not issue. The object diagram compiler is a batch program. The user has no interaction with program after starting it. There is no interactive debugger. Each error message are printed in a file. Once again, our approach was dictated by simplicity. It was simpler not to provide an interactive debugger. The batch approach has worked well in practice. Then, fifth point from this chapter, object design. Most of the work remaining after analysis was the implement association, prepare a pseudocode and write the actual code. The process of writing pseudocode uncovered several analysis flaws. We revised the analysis as needed. The design was straightforward application of object-oriented programming and mostly a matter of adding detail. It has three parts: functional model, intermediate object model, connectivity algorithm. Okay, up till now we have studied what is objective of project, what is a problem statement of that project, then analysis different steps, then system design, then object design. These five steps regarding also your mega project also. So we stop here.